I'm going to try something a little bit different today. Since it's a review session, I generally don't have the don't use the dot cam, so that the recordings aren't kind of as perfect of a substitute for class to kind of encourage to in class, because I think it's helpful to kind of see things worked out. But because it's review and I've got some people I know that are out for job fairs, things like that, I want to make sure they have kind of a little more complete review today. So the exam got it printed out. It's going to be just 20 multiple choice questions. It was very similar to those practice exams. So we'll go over a little bit today about kind of the, any question that you see on these practice exams, you can expect that be asked something similar. I might throw in a couple of additional ones that aren't on the practice exam that I think might be a good idea to know as we kind of work through it. But other than that, I'll bring the formula sheet. Make sure you have a calculator, not on your phone. Make sure you just need something to write with, and that should be really all you need. I'll bring some blank paper you can write in the exam, but I'll have some extra paper in case you want to, do your work on the side and something as well. Okay. Any questions from me? Kind of the logistics of it? Yeah. Yep. So I'll print out the formula sheet so that everyone's starting out with the same thing. Now, one thing I mentioned on Monday is, and you won't be able to use that formula sheet, like everyone's getting the exact same one. So there's nothing labeled here, but what's good practice is as you're studying for this, and maybe even just looking at this formula sheet, trying to identify what all these equations are. All right. Now, one thing that's helpful is this kind of flows in the order of the class. So we've got our population, our sample mean, population, sample variance, population, sample standard deviation, median, weighted mean, weighted variance, weighted mean and variance if we kind of have, those bins where we had to use the midpoint, covariance, correlation coefficient. Go back up here, we've got our complement rule. We've got our addition rule, right, to how to find the union. We have our multiplication rule, kind of how to use these conditional probabilities and intersections, kind of work in either direction. Here's some special conditions. If they're mutually exclusive, this is how we could find the union, because remember, intersection would be 0. Here's what would have to be hold if they're independent. Here's kind of the usable form of Bayes' equation, right? Our discrete random variable, which we said was just like a weighted mean, weighted variance, but its probabilities are our weights, so the denominator kind of goes away. We've then got our binomial functions, and we then have our Poisson. So maybe you're writing these down kind of next to it, printing it out, kind of as you're studying, kind of making those connections with those words. And then as you see like the practice exams, which equation was used on which problems, you'll kind of be able, oh, okay, this was like a Poisson problem, this was a weighted variance problem, so on and so forth. So that might be something that's useful to do, printing that out, kind of writing next to it, or if, I don't know, you want to do it digitally or something, you can do it like on a touch screen. But any other logistical questions? So I went a little bit of a side there. Okay. Any specific problems that anyone's found in the practice exams, if you've taken a look at them, that you'd want me to go over, or any just type of problem that you're kind of thinking you would have the most difficulty with? Newer stuff, Bayes' theorem, binomial. Everybody knows everything.
Bayes' theorem.
Bayes? All right, let's do an example of that. That's usually one of the trickier questions. Okay. So you'll notice this exam flows pretty close to how we cover things in class, just like the exam, right? Or sorry, formula sheet. So, question 1, you probably shouldn't be using an equation from the bottom right? It probably needs to be something that's up here. So we're about halfway through. And we kind of have this given information. So first of all, I'm going to zoom in because I can barely read this in front of me. So we've got this kind of set up with a lie detector test. Now we're asked for what's the probability the person is lying, and the test says they're telling the truth. So because I've got a couple questions here, one thing that might be useful to do is just write out the probabilities I was given so I can kind of have them to look at. I've got it written out in the context of my example, and I can answer the next 2 questions. So the information I'm given is that suppose that given someone is lying, the probability the lie detector test says they're lying is 90%. Right? So I'm going to think about this as probability that Let's see if I can remember these as we work it, right? So I've got the probability that given that someone is lying, the test comes back that shows they're lying, this lie detector test, is a 90% chance. Right? Now, whenever I have one conditional probability, and I might not need this for this problem, but just to be complete, in case I gave you one in the exam where you would, I can also find another probability, right? So remember, if we condition on the same state of nature, so given that someone's lying, if the probability that the test shows that person's lying is 90%, or probability of 0.9, what's the probability of the other outcome? Yeah, right? Those are the only two outcomes of the test. We said in all these examples, we're assuming like there's no inconclusive, right? We run the test until we get a definitive answer. Right? So that's the first two things that we've identified. Okay. The next thing says, given that the individual is not lying or telling the truth, the lie detector incorrectly determines they are lying 20% of the time. Right? So here we've now been told, okay, given that someone is telling the truth, right, or not lying, however you want to write this out, the test comes back and says that they're lying 20% of the time, right? Or we're getting false positives about 20% of the time. People who were actually telling the truth, but the test says that they were lying. So automatically, we know another probability, because if we condition on that same state of nature, the probability of the other outcome of the test, these two things should add to 1, right? Those are the only two outcomes I can see. So this probability should be 0.8. Right? And then there's only one other thing I need to know, which is the underlying probability of the state of nature. So I'm told, suppose recent studies have found that on average, people lie about 5% of things, right? So we'll go with the probability that someone's lying is 0.05, which means they're telling the truth with a probability of 0.95, right? Those two states of nature, we said they're complements. I'm either lying or I'm not, right? So those two probabilities should add up to 1 as well. So this is anything I could ever need. Any question, I could answer any question regarding Bayes' theorem now, right? So I've got these 6 probabilities. We'll kind of work through the next couple problems and kind of reference those, right? So the first thing we've got is, what is the probability a person is lying and the test says they're telling the truth? Right? Well, so write out what we want. So the probability that someone is lying and the test says they're telling the truth, right? And let's double check that that's what the question was, as I'm saying these and going back and forth. So probably they're lying. Yeah, and the test shows that they're telling the truth, right? So we know we want an intersection, right? So if we go to our formula sheet and we look up here, we're reminded that, okay, I can find the intersection of two events as the conditional probability times whatever I'm conditioning on, right? So I'm going to try to write this out in the context of my example. So I can think about it as, here's my A, here's my event B, right? So the way that equates, so we'll take the conditional probability of these two. So what do I want? The probability that the test shows truth given that the person is lying, and then multiplied by, so if you look at, I'll kind of match this up to the formula sheet in just a second, multiplied by the probability of whatever I'm conditioning on, or here would be kind of my event A. So we go back to the formula sheet. I identified my A and my B as lying, telling the truth. So I just wrote that as a conditional probability times that I'm conditioning on. I just wrote it out in the context of my example, right? Is that making sense of what I'm doing? I'm just trying to kind of show you can take that general form and I'm trying to kind of matching it up to that formula sheet, kind of our example. Yeah.
How did you know it was intersection opposed to the other two
Yep.
formulas that-
So we're on practice exam, and I forgot to mention that as well. So you've got that you're looking for the probability that a person is lying and the test says they're telling the truth. If I had a question instead, maybe like up here. Oh, I guess I didn't have one up here. Maybe might be one to add in where I asked maybe the probability of this or this other thing, right? And is the intersection or is our union, right? So that's kind of how I identify the difference in terms of a union or intersection. I also might have something where I'm asked for like, given this information or this event has occurred, what's the probability? So I could find conditional probabilities as well. Anytime you're looking for a conditional probability, you should have that word given in there, right? Given something, and I will use that, right? Not all real life or problems or word problems are going to be phrased as given this, but I'll kind of make sure I use that terminology so you can identify this is a thing that you're being told is true. You're looking for a conditional probability. So we have that and in there. Excuse me. At this point, it's just a matter of plugging things in, right? What's the probability that given someone is lying, the test shows they're telling the truth? 0.1. What's the probability that a person is lying? 0.05. All right. So I should kind of just end up kind of multiplying those two things by each other. Okay. Any questions on that before we keep moving here? So that wasn't Bayes' theorem, but I'm kind of building us up to it. Okay. Okay with this? So the next one, I ask you for another intersection, right? So we're going to just skip this problem for now, just for the sake of time today. I want to get through more examples. But then we get down to 12. So 11 is basically the same thing. It's just we have different events we're looking at. For 12, we're asked, okay, given that an individual fails this lie detector test, or the test shows that they lied, what's the probability they're actually telling the truth, right? So here we've got a conditional probability, right? Given the individual fails the lie detector test. So what are we looking for? We'll kind of write that out. Given that someone fails the test and it shows that they're lying, if I remember right, then what is the probability they actually are telling the truth? So what's the probability the state of nature is that they're actually telling the truth? So if we try to write this out in the context of kind of what we did before using that multiplication rule, I'm probably going to find out pretty quickly. So if I think about simply using this here, trying to find a conditional probability, well, my event A and B, right, were telling the truth and the lie detector test coming back positive. So will I have just the underlying probability the test comes back positive? No, I only have the probability the test comes back positive given certain circumstances. So I could write this out and quickly kind of identify, yeah, I can't really use that multiplication rule here. I'm gonna have to break this down further, which is what we did with Bayes' theorem, and I'm gonna have to use this equation here. Now, a not so technical way of doing this is the practice exams look very similar to the flow of the real exam. So if you get kind of down to the middle here, hopefully you are able to kind of identify, up here, I've got conditional probabilities just using a contingency table that I can use the multiplication rule for. But when I'm given information like this, where I've got all these conditional probabilities that were told to me, and then I'm looking for another conditional probability, that's going to be that kind of identification. I probably need to use Bayes' theorem here, right? Now you could write it out, that multiplication rule and figure out I don't have those probabilities, but just a kind of non-technical way. If you are given all these conditional probabilities, it's likely that you should be using Bayes' theorem then when you're finding a conditional probability this far down, okay? So we're going to have this guy right here, and we're just going to write this out in the context of our example, okay? So let me write this down real quick before we switch over. So all I'm going to do is take this, I'm looking at this, and I'm going to write it out using, hold on. There we go. So I've now kind of, where are we at? There we are. So there's my Bayes' theorem equation. I've identified my S and my E. I'm just going to write this out in the context of my example. So here I've got what's in my numerator. What's the probability of E given S? My S is that they're telling the truth, times the probability of what I'm conditioning on, right? Or whatever that state of nature is. Okay. I'll then identify that and I'll probably write this a little smaller because this is the exact same thing. The first part of my denominator is the exact same as whatever is in my numerator, right? We can kind of go back to that general form and you can kind of see that. That's because really what we're doing with Bayes' theorem is saying, look, we know there's going to be a group of people who are actually telling the truth that this lie detector test shows they're lying. out of how many total people will be identified as lying? Well, that will be everybody who is telling the truth and the test gave a false positive, but also everybody that the test came back showing that they're lying and they're in the other state of nature, which is that they actually were lying. I ran out of room here. Multiply that by the probability of that other state of nature, right? So probably the test shows that someone's lying, given that they actually are lying. Now we can have our two groups of people. Everybody that got a lie on that lie detector test, showed they're lying, and they actually were. And everybody where the test came back said they were lying, but they're actually probably true. Now from here, it just should be a matter of plugging in those probabilities we identified earlier, right? And just to kind of go back here, that S complement, remember, we were looking at the event S that they were telling the truth. So our S complement was that they were in fact lying. Okay. So now it's just a matter of plugging our values in, right? So we kind of come down here. Let me see if I can get this on one line. So I've got, given that they're telling the truth, the probability that the test shows they're lying, 0.2. Probability they're telling the truth, 0.95. Oh, this is not on here. Sorry, there we go. Then I want the probability that given they're telling the truth, oh, this is the exact same thing, so that's pretty easy. All right, I just plug those in. Then given that they're lying, what's the probability the test shows they're lying? We actually had that was what, 0.9? And then the probability that they are lying, underlying probability, was just 0.05. Okay. So all we did was use our probabilities that we had earlier and plug everything in. Right? And now hopefully this isn't too bad to get entered into our calculator. Any questions over any of the steps there? Like I said, I know that'll be one of the harder problems on the exams, usually Bayes' theorem, probably the binomial stuff, and then maybe some of the Poisson stuff are kind of some of the trickier questions. Okay. Any questions on that before we keep moving here? Any other types of problems you'd want to see worked through next? Otherwise, I'll kind of pick and choose. Yeah. A? Oh, yeah. So, this is going to be using a combination of things that we talked about before, which is that if I look at this entire experimental outcome space, it has an area or the probability of which should be what? 1, right? So everything in the circles and then everything outside of those circles has to add up to 1. So this is the idea. Oh, I'm screwing this up for the recording. It's all right. So this is the idea that if I looked at the probability of what's in the circles, well, that's the union of the two events. Everything outside the circles, I'm told, is the intersection of the complements. So I know that if I take everything that's in those circles or the union of those two events, and I added to that everything that was outside of them, which is told, I'm told that's the intersection of the complements, those need to add up to 1. So I'll show you where in the formula sheet in just a second, but one thing we can do is remember, oh yeah, I actually have an equation where I can find this union, right? And that's going to be, I would take the probability of each event, but then I need to subtract out what I've double counted, and that would be every outcome that's in both of them, right? So the union of two events is adding up the probability of each event, subtracting out what would be in both or what I was double counting. And then of course, we still kind of have this guy over here. Well, now if I know any 3 parts of this, right, equation, I can solve for the 4th, right? So if I go back, I've got the probability of A and B is 0.2. I'm just going to write this down as I go through these and then I'll show you. The probability of the intersection of the complements is 0.1. The probability of A is 0.4. And we still don't have what we're looking for, which is that probability of B, right? So 13, we're trying to figure out what the probability of B is. Well, all I did was kind of plug those values that I was given into that equation. Now it's just a little bit of algebra, right? So 0.4 minus 0.2 plus 0.1, that's 0.3. So I'll subtract that from both sides. And I'm left with the probability of B being 0.7. So what I'm kind of exploiting there is knowing the entire experimental outcome space is 1. So I know that the union of those two events and what's outside them, the intersection of complements adds to 1. And then using that definition of what the union is. All right. In fact, I'll show you another one that kind of goes along with this, but before I do that, if I can get this to share, there we go. A reminder of that union is on my formula sheet, right? It's the probability of both events, subtract out that intersection. Okay. Does that kind of get? So one thing that's actually a question in the Excel homework, and also there's probably a problem on the Connect, is if I go back here, let's say I had some contingency table, right? I don't think it's too bad finding intersections on this table. Hopefully those are like some really easy problems on the exam. I mean, if I ask you here, what's the probability that person is 55 or older and they don't favor legalization of marijuana? Well, they're older than 55, they don't want marijuana legalized. Those top four cells, those tell me the probability of the intersections of those two events. So that's as easy as just going up there, saying that where those two things meet, 0.11 is that probability. Okay. Any questions on that? I mean, that should be a really easy kind of question, hopefully, on the exam. Now, if instead, let's say I asked you, what's the probability that a person is 55 or older? Oops, it's going to let me edit this. What? Oh, I've got it on read only because I downloaded it. All right, well, imagine I replace this with or, right? So I want the probability that a person is 55 or older, or they don't favor the legalization of marijuana. So what I'm thinking about there is the probability that someone's older than 55. I think I was calling this event O, and then the union, right? Or they don't want marijuana legalized. So legalized marijuana equals no. Just kind of use that as my shorthand. Right? So if I have the union of two events, we just said, then I would take the probability of each event, subtract out that intersection. So what I'd be thinking about here is what's the probability that someone is older than 55 plus the probability they don't want marijuana legalized, and then subtract out the intersection of those two things. Okay. So all I did was I'm looking for a union, right? And write that out as the probability of both events minus what I double counter to subtract the intersection. Now from here, hopefully this is fairly easy, because if we go up here, okay, what's the probability that someone is older than 55? Well, that would be in our total, right? The probability they're older than 55 is 0.25. So I'm just going to write that in and we'll kind of switch over in a second. I then would want, okay, what's the probability of the other event, which is that they don't want marijuana legalized. So that would be kind of down here as 0.34. And then if I subtract out their intersection, right? So here's their intersection, right? Which is that they're older than 55 and they don't, so 0.11. Well, now hopefully, I've got those three probabilities. I plug them in. That's what I wanted. This should be relatively easy. I don't know what there's a 0.48 if I'm looking at this right. No, 59. Yeah. Okay. So I think it helps when we're working through all these, writing out what what you're looking for in the context of your example. You'll have those formulas in front of you as kind of the general form, but writing out in the context of your example kind of helps make a lot of sense. And you're asked to do something that's like this on Excel. There isn't a question on the practice exam, but just because, the practice exam isn't going to be every single type of question I could ask you, right? So, you should know how to find the union using this contingency table as well. Because one of the things you should know is that you can rewrite the union as the probability of both events, subtracting out the intersection. And we use that definition to kind of help us on 13 as well, right? We rewrote that union. Anybody else have a type of question or problem they want to see worked through? Nobody? Yeah.
What's your office hours?
So I'll be in my office from 2 to 4 today and tomorrow. There's a slight, well, I don't think I'll have to change it tomorrow, but if I do, I'll get an email out early in the morning. But yeah, it should be 2 to 4 today and tomorrow. question, specific problem. Yeah.
The binomial distribution one.
All right, let's go down. Let's get this on the same page. Maybe. No, never mind. So we've got approximately 64% of people have a visual impairment and need corrective lenses or surgery. Suppose you select 15 people at random. What would the expected number of individuals be who was visually impaired? Right? So remember, once we go to discrete random variables, we're not really calculating means. I mean, we call it the mean, but we're really calculating expected values, right? This is the expected value of this random variable. So we use the mean and kind of expected value interchangeably, kind of moving forward. But here, the expected number of individuals, that's just the mean of your binomial. Well, hopefully, if we go back to our formula sheet, we scroll down. Okay, if I see a bunch of factorials, hopefully I'm recognizing this is my binomial kind of set of equations. Notice I'm even being nice and kind of grouping those here together. So how do you find the mean for the binomial? That was that intuitive thing where we just took the number of trials times the probability of success. So for us, that would be what? 15 people is our number of trials. The underlying probability of success of any one person, needs corrective lenses is 0.64. So 0.64 times 15, I'm guessing that's 9.6. All right. So that would just be how we find the mean for a binomial. What if then instead I'm asked, what's the probability that exactly 10 people have a visual impairment? Okay. So I want the probability that X is equal to 10. Right? So this is what I'm looking for. My number of trials was 15. My probability of success, or that someone needed corrective lenses, any one person, was 0.64. And here my X, I'm looking for the probability that's equal to 10. So I'm just going to plug in my values to that binomial. So I'll have this pulled up, my formula sheet. I can see, okay, if I've got a binomial example, right? Someone either has corrective lenses or they don't. So I've got a 1-0 success failure. I've got an underlying probability of success. If I chose any one person out of 15 people, so I have a max number of successes I could see, this will give me the probability of seeing any specific number of successes. In this case, we wanted 10 out of 15, right? So all I'm going to do is start plugging in my values here. My N is 15, my X is 10, my P was 0.64, right? So I just start writing this out. N factorial over X factorial and minus X factorial, probability of success to the X power times 1 minus that probability of success. Hopefully you guys can read this. If you can't, make sure you ask me what I've written down. So to the N minus X, right? Or 15 minus 5. Now, generally, yeah. Or sorry, it's not 5. We're doing 10, aren't we? Thank you. Because I wasn't looking and I was, there I go. That should make a little more sense, right? Thank you for asking. Okay. Sorry. Yeah, so what this have given me is the probability that X is equal to 5. Sorry, that's not what we wanted. We wanted the probability X is equal to 10. So I've got this plugged in. I just start doing the simple math in my head if it's me, and I just write this out. So just to simplify, get rid of some of this, I can do 15 minus 10 in my head. I can do this. So this is what, 0.36 to the 5th power. Just to make my life a little bit easier, I would simplify it right away. Right? Now from here, hopefully you've identified where that factorial button is on your calculator. Or if I wrote this out, I would see, even if I didn't have that button, and times 9 times 8, etc. 5 times 4 times 3 times 2 times 1. Everything from 10 on down here would cancel. And I just have 15 times 14 times 13 times 12 times 11 divided by 5 times. I could do it that way, right? Or if I have that button in my calculator, I can just kind of enter in those factorials. Right? And then, of course, I have this here as well. Right? So generally what I might do if I was working on this problem is break this down, figure out what this fraction is. Then I would only have one number, put this in my calculator, have another number. I kind of break it down to intermediate steps. So, if you wanted to do this, I don't know what this number ends up being. But if you enter this in your calculator, write that number down, enter this into your calculator, Write that number down. Now it's just simply multiplying those two things by each other. Or you can enter it on one line if you're feeling comfortable with that. Any questions on that before we keep going here? We're okay with this? No questions over anything that was done up here? Went through it kind of quick. Yeah.
And then remind me again, the factorials,
Mm-hmm.
the 10 and the 5 on bottom,
Mm-hmm.
you're just gonna run together.
Yeah, so if I wrote this out to be truly complete, it would look. And then I'm just multiplying. So it's, sorry, not 0.4, but. Right. So I could just one multiply every number by every number, right? 10 times 9 times 8 all the way down to 1 times 5 times 4 times 3 times 2 times 1. Now that'd be a really large number, right? Which is, fine. But I could also have canceled a lot of things to kind of make it a little bit easier on myself. Yeah.
That's the PRB button, right?
Yeah, on most calculators, if you go to the PRB button and then over, it's usually the third option. And it's like an exclamation point. So you would hit like 5, or sorry, in this case, 10, second, go over to that exclamation point, select it, and then hit enter.
When you're putting that in the calculator, could you divide that? Could you do that function the same, the probability divided by, or the top factorial divided by the.
Yeah, you can do that. You'll have to make sure, depending on what calculator you have and how you're hitting the enter button. We need to be careful with the order of operations, that you need to make sure you're dividing by like that, right? So like if I get lazy and I go 15 factorial divided by 10 factorial, I hit enter. Well, then if I was like, or somehow had multiplied by, then I hit multiply by 5 factorial. Well, then it's multiplying, it's actually doing this. Right? And this isn't in my denominator, it's actually in the numerator. So you need to make sure that you're using parentheses or making sure that, I don't know, it depends on what calculator you have, that you're doing it in such a way that your order of operations is that you're first multiplying these two so that you're dividing by whatever that entire product would be. Any other questions on that one? We'll do one more example here too with the binomial. So let's instead think about one where we've got to use some other rules. So what's the probability that less than 14 people have a visual impairment? And just for the sake of this, we'll probably have time so we can do it. So let's say I want the probability that's less than 14, right? So there, I'm just going to write out what I'm looking for. I want the probability X is less than 14. Right? Well, we said that if we ever have like multiple outcomes in our event for the binomial, since everything's mutually exclusive, right? I either see exactly 14 people have a visual impairment, exactly 13, etc. This would just be the probability of every outcome that fits this criteria. So what's the very first number of successes that meets this criteria? 13. Yeah, right. I have strictly less than. It's a discrete random variable, right? Binomial, I either see a success or I don't. So the probability that X is equal to 13 plus is equal to 12, all the way down to the probability it's equal to 0. So I now use the binomial function to find every single one of these probabilities. There's no way I'm going to have enough time to do this on the exam. So this should be an indicator that there's something else I can use, we talked about, which is the complement rule. If this is my event A, well, I can rewrite that as 1 minus the probability of a complement. What would a complement be? X being greater than or equal to 14? Well, out of 15 people, what are the only 2 possible outcomes that meet this criteria? Well, X could either be 14, or I could see all 15 people have a visual impairment. Well, now I only have to use that binomial equation twice, which should make it a little bit easier. Okay. So if you have something where it's like, seems like if this takes, this is going to take me way too much time for this exam, it's probably because you can rewrite it using a complement. And that might be even nicer on the exam where I kind of have it so that there's only one, like, maybe I asked the probability you were less than 15, right? Okay, well then I only have one probability to find. But now, if I didn't, right, I can just write this out in the context of my example. So to find the probability X is equal to 14, I would probably break this down to steps, but I would have n over x factorial and minus x factorial probability of success to the x times 1 minus the probability of success to the n minus x. And then I would have to add in that same thing, but for probably x is equal to 15. Right? Now, I would probably break this down and do it, separately. So I'm first going to find this. There's a lot of things you can kind of notice here that are going to simplify. This just becomes 1 factorial. Well, dividing by or multiplying by 1 doesn't change anything. So what I've really got is 15 times 14. I could write that out 0, 14 times 30. Everything's going to cancel except for that 15. Right? You can enter that in your calculator if you want to prove that to yourself. All right. And then it becomes a little bit easier here. I'll just simplify things down. That should give me the probability that x is equal to 14. And then we said a real nice trick. You can just remember this. Now, if you write it out, I'm going to write it out and show you that it cancels. But we can kind of use the end result to, the amount of choice. So if I ever want the probability that they're all successes, this becomes pretty easy. Because if I start writing this out, if I want x to be 15 as well, so my n and my x are the same thing. Right, because n minus x, 15 minus 15, I guess I should write this out. 15 minus 15. Well, that's just 0. Anything to the 0 power is 1. Multiplying by 1 doesn't change anything. 0 factorial is 1. 15 over 15 factorial cancels. This whole thing cancels. If we ever want the probability that all of them are successes, it's simply that underlying probability of success to the power of however many trials we have. So this would give me the probability that x is equal to 0. And I can write out the entire binomial equation every time if I want to, and then just see that all these things cancel. But if I remember that ahead of time, I can always just use the fact that if I want all of them, I want the probability that all of these trials are successes, it's just the underlying probability of success raised to the whatever power the number of trials I have is. Any questions on this before we keep moving? So I kind of combined the binomial and kind of complement rule there. Now, one thing I'll point out, just more of a test taking thing. Don't get too lost in these equations because a lot of the other answers that are up here, like I'm not just randomly choosing these. I'm writing some of the answers to be like some common mistakes you could make. So some of these might be things that you end up getting in your calculator, right? But if we stop and think about what we're doing, so we can prevent ourselves from making some easy mistakes. So for instance, maybe I just went through that one. I found the probability. I don't know what this is. If anyone found it, you can kind of shout it out, let me know. All right, so anyways. So we have these two probabilities, right? Whatever they work out to be. And I add them together and I think I'm done. Well, I forgot the whole thing, where I started was, I had to find those and then subtract them from 1. So I could end up with like a pretty small probability. If I go back and think about what I'm doing here, well, I already found that about 9.6 or just about 10 people have, I'm expecting have corrective lenses, right? Or if I even think about 64% of 15, I know it's going to be somewhere around the middle value. Okay? So 9.6. So the most likely outcomes will be what? We said if we've got the mean, the most likely outcomes, or the two outcomes that have the highest probability of occurring, will be the values on either side of that mean, if it's not an integer itself. Right? So 9.6, 9, and 10 are going to be our most likely outcomes. So as we move further from that number of successes, we're going to see the probabilities decline. So by the time I get to being, what's the probability that remember what I'm asked for here. What's the probability that 14 or fewer than 14 people have corrective lenses? Well, that would be the probability that x is equal to 13 plus 12 plus 11 plus 10 plus 9. Well, I know that 9 and 10 are my most likely outcomes. And then the next most likely would be 8 and 11, 7 and 12, 6 and 13. All of those probabilities are in the area I'm looking for, right? I want the probability x is less than 14. That includes 13, 12, 11, all the way down to 0. So just before we even get to an equation, just think about what we're looking for. This probability should be relatively high or low. So probably should be relatively high, right? It includes our most likely outcomes, right? It includes 9 and 10, and it includes our next most likely outcomes, which would be the next number on the other side. So 8 and 11. Who's the next most likely? It includes, in fact, 14 of the possible 16 outcomes we could see. Remember, gonna have to count that probably x is equal to 0 as well. So I should be thinking this should be a relatively high probability. Now how high is relatively high? I don't know. I'm thinking probably 0.8, 0.9, somewhere around there. And if I look at my my answers, and I'm probably thinking it's going to be either C or D, right? Those other probabilities don't make a lot of sense. Now, what's going to be true is when I go ahead and find the probability x is equal to 14 and the x is equal to 15, I add those up, I believe it's 0.012. So if I forget to then subtract it from 1, I might select the wrong answer. But if going into the problem, I remember, well, this probability should be relatively high when I calculate it. Then that can kind of help me remember, why did I get such a low probability? I look back and oh yeah, I was supposed to subtract it from 1. I just kind of got lost in that second part of the problem. So always kind of take a step back and like think about what you're finding. I'll even point out some real easy mistakes here at the very top. Well, I'll use the weighted mean to even prove a bigger point. So here I kind of give you like, here's some class, here's the score that we got in these different categories, here's the weight of every category. Similar how I'm going to calculate your mean at the end of your mean, your grade at the end of the year. Okay. So we want to find a weighted mean for what the score was in whatever class it is. Okay? So I'm going to use these weights as my weights, right? Making this one pretty easy. And so I could go ahead and calculate it. Now, before I even get to the calculation, right, look at the formula, I'm finding, remember, their weighted mean score. The mean, the median are measures of central tendency. So this should be somewhere in the middle of my data. If I look at these scores, what can I bound this weighted mean by? Like, what are the upper and lower limits that it could possibly be? Yeah, somewhere between my maximum and my minimum value, right? I'm looking for the middle point. It's got to be somewhere between the maximum and the minimum. Right away, 321 and 25.61. I've got a 50-50 shot now, even if I don't use the formula, right? So I try to write these so that you use the principles or kind of take a step back from the formulas and think about what we're trying to find. A lot of the times you can rule out some of these answers, right? And it's not going to be, necessarily make sure that you get the correct answer, but it's going to, over the entire exam, increase the likelihood you get more correct answers, right? So, we could even do this like you could do a binomial kind of, you get the question right or wrong. How many questions out of 20 do you get correct? And if you increase that underlying probability of success by just randomly guess, my probability would be 0.25. If I know just some basic principles about the statistics I'm looking for, and I can rule answers out, well, then not even doing the work, I can increase that underlying probability to 0.5. Then I expect a higher number of questions I get correct on the exam, right? So make sure that you don't get too lost in those formulas. Take a step back and think about what you're looking for. Same kind of thing would apply up here. If I'm looking for the mean age of fighters, and I've got 178 here, that doesn't make any sense, right? My ages here are going to be somewhere between 28 and 41, right? My minimum, my maximum value. All right, so right away, this one I can kind of rule out. I've got it down to 3 options now, just increasing that chance that I get it correct. Any other questions before we keep going here? That's 6 minutes. I'll probably try to do one more. So, a couple things I want to point out. Make sure you're reading these carefully. I try to do things like highlight or bold, right? These words that are important. So, for instance, this is a sample standard deviation. What was the only difference in the calculation for the sample and population variance or standard deviation? Instead of dividing by n, what we do for the population, we divide by n-1 for the standard deviation of the variance, right? And that's, we're reminded of that. Excuse me. Up here in our variance and sample variance equations. Now, don't confuse that with the mean. The population and sample mean are calculated the exact same way. We always divide by the number of observations we have there. So the whole reason why we're dividing by n-1 for the sample variance was because we need to account for the fact that there might be additional variation once we get to things like confidence intervals, hypothesis testing after this exam. Okay. Any other questions specific here? So one thing that doesn't show up on these, here, I'll try to think of things that might not show up on these practice exams that would be good things to know. Okay. So one thing that we went through on Monday that you wink, wink could be expected to know for the exam is how to change time intervals. So for instance, here, I've got the number of people struck by lightning is 3, right? So I'm given, I kind of have this length of time, this interval, and I'm looking for the number of successes, the number of people that get struck by lightning. I'm told the average is 3, and the time period is over a year. Right? But what if I'm asked for what's the probability that one person is struck and killed by lightning in the next month? Okay. So I've changed the time interval. We said, what do we need to do? Well, I need to update my lambda so that I can get what the average number of people struck every month would be, right? Well, here, hopefully this isn't too bad. We're going from a longer, right, a year to a shorter time interval. So I want to make that average smaller. I know that. So if I want to make something smaller, would I divide or multiply it by something? Oh, by an integer. Divide, right? Well, what's my factor? How many months are there in a year? Yeah, so it's just 3 over 12, right? So I've got my new lambda is 0.25. Now it's just a matter of go to that Poisson distribution equation, plug in my lambda of 0.25, plug in my x value of 1, right? So lambda to the x, right? Remember, we wanted just one success. E to the negative lambda over x factorial, right? So I, might give you a question like on the practice exams where I give you the average rate over a year and ask you for the probability. You see a certain number of people struck by lightning in that year, right? Keep the time the same. Then it's a matter of using that, plugging in my lambda next. If I change the time, so I might do that, and then I might ask you another question where I change the time interval, right? I might give you the average rate over the year, but then I ask you, okay, what's the probability to see this many successes in the next month, right? Go to a smaller time interval. And if that's the case, this is all all you have to do is update that lambda, update that mean rate, right? You don't want the average over a year now, you want just the average over a month. Okay. Questions on that? Yeah.
You said it was mostly multiple choice.
So it's going to be all multiple choice. Yep. You don't have to show your work. So I don't do any partial credit. I've done it multiple ways. Grades end up being about the same either way because there's advantage of the multiple choice where if you don't know what's going on, you still have a chance of getting it right. Whereas on a short answer, if you have no idea what's going on, you're probably not going to get partial credit for it. And then kind of vice versa. So there's pros and cons of both. The grades end up being about the same either way. Yeah. Before you guys, any other questions before you get out of here? Yeah.
Like you suggested when we're studying, are we allowed to use that?
No, so I make it just my way of making sure everyone's starting out has the same information in front of them. I get formula sheets in other classes and like notes, and you're putting effort in, so you should, but my view of it is we should all be starting out with kind of this, same information. But it's helpful as you're studying. That's one reason that's And what I would also suggest is if you do that, as soon as I hand out those formula sheets, if there's some ones that you always can't remember, fill those, write down next to them right before you start, and that's one thing. Before you get out of here, it's not for credit today, but I'm interested and we might do some things with this in future classes, looking at some correlations between who attends review sessions and the grades they end up getting. Right? So I might do something, I'm planning to do something throughout the semester, kind of see what's the connection of attending this review session and kind of how much it improve, hopefully, the exam score, or your exam scores, which is people is getting. So make sure, I'm just getting you recorded. So any letter, just wanting you to get, as recorded for being here today. Once you answered, hit the button, you're free to go. Yeah. Oh, I got you. I got you.
Said you have office hours at 2 today?
Yep.
Is it alright? Can I come right after?
Yeah, I should be there right. Okay.
Sounds good.
Okay.
Grades, the current assignment related to
Yeah, so I don't have to go over the whole Because that way, some of the stated. After the.
That's so like the grade.
Not right now, so, generally, like, they're pretty close, but, I'll always actually take them, like, once I have them integrated, and I'll kind of. Move things around, to get a better idea of what you're trying to do. Does that make sense? Yeah.
Thank you. Emails do about like. Spring ones.
Oh, yeah.
True.
Last thing here, let me- so I'm guessing I know what it is. So. I'm guessing that you don't have it registered under your iClicker account. I can kind of check to see if that's the case. All right.
Yeah.
Yeah, so it's not showing up. So my guess is you're one of these.
Okay.
Right? Now I can identify it as soon as you get it registered correct. So what you need to do, and you can, I can kind of show you. If you go, and there's a link on one of the announcements in Canvas that's about iClicker, it's for student login. So you'll log in, then you'll go, there's like an icon in the upper left corner. It's like, looks like a notepad almost. You'll click it, go to profile, and then there will be a register remote under there, and you click the register remote there as well.
Okay.
Is that, so yeah, if you go, here, I'll kind of show you the announcement. So it's right here. This very first, sorry, actually, it's the second one. Right? You'll sign in here. There'll be an icon up here that you'll click on, then profile, register your remote. And then once you've done that, let me know.
Okay.
Send me an email, let me know you've done it. I'll resync, make sure that I now have your, and then I can backfill everything.
Okay.
Because I've got your old responses. It's like I said, it's gonna be one of those
Okay.
remotes that was sitting there at the bottom.
I got you. All right, I
Okay.
appreciate it. Thank you.
Yeah. Yeah, so remember, we did an example like this with the what was it on? It was on the union data, but
This one be the one where for like 1 minus.
yes, yep. So you can use the fact that like the complement rule, like kind of like we did today. So let me make sure that it's up there. Where did I do that? Maybe let me download this and look at it real quick. I know it's in an old Excel. Oh, maybe I didn't. It did it in class.
I remember doing it in class.
Let me see. But yeah, you're gonna use it. So remember in that equation, you can make it cumulative. So you can find the probability being less than a certain value. So that if you want the probability being above, you know that it would be 1 minus probability is less than that. Like, so let me see if I got a. I don't think no, here, I'm glad you asked me because I didn't realize, I don't think I put this up on after we worked on it.
I was also wondering because once I do that, I get 0 as an insert.
Yep, so that's right. So it's just gonna be really small. I can see your formula, like I know that seems weird, but yeah, it should be really, really small. Let me upload this here as well.
What about the one up here where it's
So then that one's gonna be a little bit trickier. So I want the probability being like less than between 5 and 10. Well, if I find the probability being less than 10, then I subtract out the probability being less than 5, I'll just be left with what's in the program. So you can use that binomial equation twice, once to make it cumulative and put. So it's between, so you don't want it to be 5 or 10, you actually only want it to be 6, 7, 8, and 9. So use the binomial function one, making cumulative for 9. That'll give you the probabilities. Oh, I said between actually. Okay, so you'll use 10. Sorry. So you'll use 10, find that probability, and then subtract out. You want to include 5. So instead of using 5, you then subtract out that binomial function using x is equal to 4 cumulative. Okay. Does that make sense?
Yeah.
So both will be cumulative, 10, 4, subtract the smaller.
Okay.
Sound good?
Yeah. Awesome.
Yeah, I know that one's throwing a couple people off, but it is so small, but that is what it is, so.
Thank you.
Yep.